So this is cyclic decomposition and a rational form. Okay. So they will try to break up V with in some T cyclic subspaces. Decomposing V into some T cyclic subspaces. Okay. So suppose we have an invariant subspace W. Okay. The fundamental question is that can we find a W prime such that V is W direction W prime and W prime is also T invariant? So that is one question. That will not happen for every T invariant subspace W, but it will happen for some T invariant subspaces. Okay. So uh, let us suppose that uh, V is W direction W prime, and these are both T invariant subspaces of V. See what we can discover about the subspace W. For each vector beta in V, you have gamma and gamma prime in W and W prime. And we know that Ft beta is Ft gamma plus Ft gamma prime. Now this is in W prime and this is in W, right? Because if W is invariant under T, then it is invariant under any polynomial in T. Now, therefore, Ft beta, see this is very important, is in W if and only if Ft gamma prime is 0, this part is 0. What interests us is seemingly an innocent fact that if Ft beta is in W, then Ft beta is equal to Ft gamma. Now, this may look like a very innocent fact, but actually what they are trying to say is that if Ft beta is in W for some beta in V, then there exists a gamma in W such that Ft beta is equal to Ft gamma. Okay. Now, look at the definition. That is the definition of a T admissible subspace of V. W is a T admissible subspace of V if W is invariant under T, and if T beta is in W, then there exists gamma in W such that Ft beta is Ft gamma. And we have already shown that if W is T invariant and it has a complementary T invariant subspace, that is it has W prime such that V is W intersection W prime and each of them are T invariant, then W is T admissible. We have already shown that. Now we will show the converse as well. That if W is T admissible, then there exists a W prime which meets the requirement. Now let us indicate how admissibility property is involved in the, yes, the inductively select, yeah. Okay, I would just give me a minute. Let me see. This proof is actually cyclic decomposition theorem 233. Oh, we will have to skip this proof because this is extremely big. Generalized clearly Hamilton, this we will do. Don't worry about that. Okay, so first let's see what they are actually. I mean, okay, let's see the path. Okay, why are we suddenly interested in those admissible subspaces? So they are saying that we will be to inductively select such vectors such that there is a vector such that wj is like this. Okay, we would like to find a non-zero vector alpha j plus 1 such that this happens. Then we will define alpha j plus 1 in this way. Okay, and this, since v is finite dimensional, this approach will terminate after finite number of steps. So that is their approach. Okay, and the beautiful thing is that they will prove this theorem. Now I would request you to read this statement of the theorem very carefully at least 2 to 3 times. This is the most important theorem, I feel. I mean, this is the goal of what we have done so far. The whole chapter 6, they lead up to this cyclic decomposition theorem. Read this very carefully. This thing. I mean, Okay. So, what is the statement of the theorem? Let T be a linear operator on a finite dimensional vector space V and W not be a proper T admissible subspace of V. Okay. There exist non-zero vectors alpha 1 to alpha r in V with respective T annihilators P1 to PR such that this happens and Pk divides Pk minus 1. Now, one immediate observation is that W naught has to be a proper subspace of T admissible subspace of V, right? I mean, you can't just take W naught equals to 0. I mean, can you take that? This is, I mean, I hope by proper subspace they mean non-trivial subspace as well. Otherwise, any over any field, this has a. Okay, let's see what they do. I mean, can W not be 0? Yeah, this. The proof is rather long. Hence, we shall divide it into 4 parts. First reading it may seem easier to take W not equals to 0, although it does not produce any substantial simplification. Throughout the proof, okay, we will skip the proof, but this extremely important statement. One immediate corollary is that let T be a linear operator on a finite dimensional vector space V. There exists a vector alpha in V such that the T annihilator of alpha is the minimal polynomial in T. Such that the T annihilator of alpha is the minimal polynomial for T. T has a cyclic vector if and only if the characteristic and minimal polynomials of T are identical. If V equals to 0, the results are trivially true. Let V equals to this. Okay. So they have taken a decomposition of V where the T annihilators P1 take a PR are such that Pk plus 1 divides Pk. Okay. 1 to K to R minus 1. As we noted in the proof of theorem 3, it follows easily that P1 is the minimal polynomial for T. Because you see that every Pi divides P1, right? This P1 is the minimal polynomial for T. So generalized Cayley-Hamilton rational form is next. Invariant factors. Example 4. Yeah. So let's see what is generalized Cayley-Hamilton. Okay, so so we know the Kelly-Hamilton theorem. They say that, I mean, they are proposing this generalized version that if T is a linear operator on a finite dimensional vector space and P be the minimal polynomial and if be the characteristic polynomial for T, P divides F. Okay, P and F have same prime factors except for multiplicities. If P is F1 to the power T1, and this is the prime factorization of P, then F equals to F1 to the power D1 dot 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 Fk to the power Dk, where Di is the nullity of Fi to the power T to the power Ri divides the degree of Fi. Okay. So if P is F1 to the power R1, I think written there, R1 to Rk, D1 to Dk, where Di is the nullity of Okay, so let's see the proof. We disregard the trivial case this. To prove 1 and 2, consider a cyclic decomposition of V obtained from theorem 3. As we noted in the proof of the second corollary, P1 is P, right? Let Uy be the restriction of T to Z alpha I T. Then Uy has a cyclic vector. Okay? And so Pi is both the minimal polynomial and the characteristic polynomial for Uy. Therefore, the characteristic polynomial f is the product f equals to P1 to Pr, that is evident from the block form. Yes. And this proves 1. Obviously, for any prime factor P is a prime divisor of f, conversely a prime divisor of f is this. Must divide one of the factors Pi, which in turn divides P1. Now, let 7.16 be the prime factorization of P. We employ the primary decomposition theorem. It tells us Vi is the null space of Fi to the power Fi t to the power Ri. Yes, that is the primary decomposition of V. Is the minimal polynomial of Ti obtained by restricting T to invariant subspaces, right? Of the present theorem to the operator Ti, since its minimal polynomial is over a power of the prime Fi, the characteristic polynomial for Ti has the form f to Fi to the power Ti Di, where Di greater than equals to Ri, of course. Di is dimension Vi to the power degree of Fi, because because Fi to the power Di is the null, is 0 applied on Ti, and almost by definition degree of Vi is nullity of this. Corollary: T is an equipotent linear operator on a vector space of dimension n, then the characteristic polynomial for T is x to the power n. example. Now, let us look at the matrix analog of cyclic decomposition theory. We have an operator T and direct sum decomposition of 3, where beta I is the cyclic ordered basis, okay, of Z alpha I T, of course. Ki denotes the dimension of this. That is the degree of the annihilator of Pi. The matrix of the induced operator Ti in the ordered basis beta I is the companion matrix of the polynomial Pi. Thus, if we let beta be the ordered basis of V, which is the union of beta I, then T in beta looks like this, where Ai is the Ki cross Ki companion matrix of Pi. Okay, this form will be said the rational form. Matrix is a non-scalar matrix. Pi divides I plus 1 divides Pi. This is called the rational form. The cyclic decomposition theorem tells us about the following concerning matrices. If be a field and let B be an n cross n matrix over F, then B is similar over F to one and only one matrix which is in the rational form. If is a field and B is an n cross n matrix over F, then B is similar over the field F to one and only one matrix which is in the rational form. You understand? You can't permute the basis. Like you just permuting the vectors in the basis and getting new matrices, that won't work because of this criteria, that Pi plus 1 must divide Pi. Okay, so you can't just write V. Suppose V is like Z alpha 1 comma T direct sum Z alpha 2 comma T. Okay, so P2 divides P1, right? So you can't just swipe it. You can't write V like Z alpha 2 T direct sum Z alpha 1 T. I mean, this is true, but the problem is this is not a cyclic decomposition, because then you should have P1 divides P2, which may not be true. Okay, this is the reason you get the uniqueness of the rational form. So this uniqueness is very, very important. Okay, so I will give you a few minutes, maybe 7, 8, to look at these examples, right? Example 2, 3 and 4. Please have a look at them. You have a few minutes. All of you have the book, right? Please have a look at this 2, 3. Example 4. Yeah, please look at this. These 3 examples. Or 2, 3 at least, we will discuss 4 maybe. Okay, so let's have a look at example 4. So suppose T is a diagonalizable linear operator on V. It is interesting to relate a cyclic decomposition for T to the basis which diagonalizes the matrix T. Let C1, Ck be the distinct characteristic values, okay, and Vi be the characteristic subspaces associated with that, blah 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 blah. If is this. Now we have seen in one of the exercises of the previous section that this is a cyclic vector, right? For every polynomial given any scalars, there exist polynomials if such that if Ci is Ti. Yeah. Yes. So what they are doing is that they are picking up one characteristic vector from each of the characteristic subspaces. Okay, that is your Z alpha. And they go on to create this subspace Z alpha 1 to this. And let me tell you, I mean, how this will look like. It will look like this. I mean, the first block will be appearing each of the eigenvalues exactly once. Okay, now the second block will be, I mean, appearing eigenvalues which are two or more times. The next block will be eigenvalues which have appeared three or more times, and so on. Okay. So let's try this problem. Like this one. T be a linear operator on F2, which is represented in the standard order basis by the matrix this. Okay. Let alpha 1 is 0 1 show that. Okay, you guys try this problem for 2 minutes. Hello. Hmm. 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 তোমার কোন নাম্বারটা লিঙ্ক করা আছে? দুটো ব্যাংক কি সেম নাম্বার লিঙ্ক করা আছে? তাহলে হয়। হ্যাঁ, সে করে দেবো। দুটো ব্যাংকই সেম নাম্বার থাকতে হবে, তবেই হয়। না, ধরো যদি এরকম হয় যে তোমার 4টে নম্বর, তাহলে কি, তাহলে হয়ে যায়, তাহলে কোনো ব্যাপার না। তাহলে কারণ কালকে আমার হয়তো 7টা থেকে অনওয়ার্ডস থাকবে। সকালে আমি কলেজ যাবো। হ্যাঁ, সন্ধ্যাবেলা। হ্যাঁ, সকালে আমি কলেজ যাবো, তারপর আমার কলেজ ছুটি হবে। দেখুন, শনিবারের মধ্যে একদিন হয়ে যাওয়া উচিত, হ্যাঁ, ঠিক আছে? হুম। তোমাকে একটু সকালের দিকে, একটু সকালের দিকে বললে তাহলে সারাদিন টাইম পাওয়া যায়। তখন আমি একটা দিয়ে চলে যাবো। কারণ না, না, সে করো না, যখন হোক আমি চলে যাবো ঠিক করে। মানে আমি বলছি রাতে করলে কি হয়, রাতে আমার পড়ানো থাকে তো এখন আর বেরোতে পারি না সেখান থেকে। সকালে বললে সারাটা দিন সময় থাকে, একটা তো 5 মিনিটের জন্য চলে যাবে। They say that let alpha 1 is this 0 1, show that if square is not this and that there is no non-zero eigenvector alpha 2 such that this is disjoint from this. Okay, so let's try to do it. If 2 is not alpha 1 t. Okay, let's see how they do it. So this is in the kernel, right? This thing is in the kernel. I mean, this f square thing, sorry, f square thing, alpha 1 is in the kernel. I will call it, let alpha 1, I mean, t alpha 1 belongs to car t, na? Alpha 1 belongs to car t. So clearly, alpha 1, I mean, t alpha 1 is 0. So alpha 1, t alpha 1, this doesn't make sense because this is 0. So z alpha 1 t is basically nothing but alpha 1. So this is not f2. Now, is there another alpha 2 such that which is disjoint from alpha 1 t? Is there anyone? Now the problem is that let's see whether there is an alpha 2 or not. So what if there is one? Now see, so if f2 is like, I mean, if there is some z alpha 2, so this has dimension 1, I mean, this has dimension 1. Now f2 has dimension 2. So if there is an alpha 2, then z alpha 2 t has dimension, I mean, this is dimension of this is again 1. So this will be generated by z alpha 2 will be generated by some alpha 2. Okay, so v will be alpha 1 direct some alpha 2, but you know that, I mean, the minimal polynomial here, I mean, the polynomial here must divide the polynomial there p1, right? And we have seen that t alpha 1 is 0, which means p1 is x. So p2 divides p1 implies p2 is x as well, right? So suppose if alpha 2 is a comma b, then t alpha 2 is what? It is like a comma 0, I think, and it is 0 because alpha 2 has to be in the kernel, so a equals to 0. Thus alpha is of this form 0 comma b. But you see, then alpha 2 becomes b times alpha 1, right? Which is then alpha 2 is in z alpha 1 t. which means they are not disjoint. Okay, so if I have to write, let's write the solution a bit carefully. T alpha 1 is 0, which implies Z alpha 1 is, this implies if there exists alpha 2, then dimension Z alpha 2 T is 1, which implies Z alpha 2 T is generated by alpha 2. Since P2 divides P1, but Z alpha 1 is and T alpha 1 is 0, this implies P1 is X and P2 divides P1 implies P2 is X. So if alpha is A comma B, T alpha 2 is 0 as Z alpha 2T has dimension 1, which implies T A comma B is 0 comma A into 0 comma 0, which implies A equals to 0, which implies alpha 2 equals to 0 comma B, which belongs to Z alpha 1T. So no alpha 2, so Z alpha 2T intersection Z alpha 1T is not equal to 0, is not non-trivial. I mean, it is non-trivial. Okay, so how about doing, let's do 2. Okay, try 2 for 2 minutes. So let's try to solve this. So so the problem is like this. So T be a linear operator on a finite dimensional vector space V, and let R be the range of T. Proves that R has a complementary T invariant subspace if and only if R is independent of the null space T of n of T. And if R and N are independent, proves that N is the unique T invariant subspace complementary to R. If R is then from rank nullity, we know that R dx from N is V, and N and T are obviously T invariant. Conversely, if R has a T invariant subspace R prime, let beta belongs to R prime, then T beta is also in R prime, right? But T beta is also in R. It implies T beta is 0 and beta belongs to natural number. I mean n, not natural number, sorry. Since V is R direct sum R prime, this implies R prime is n. Let R prime be any T invariant subspace complementary to R. From the proof of the above, we say that R prime is n given R an independent. Okay. See, we won't proceed much further today. I mean, the attendance is horrific. So try this problem. So we will do again things in the next class. And before that, please vote there. I need to know which of the classes you actually need. Because I mean, with 2-3 students, it's impossible to conduct it. Like in the Galois theory, the I ring and ring theory, the I mean the attendance is significantly high.